Today, we're going to unpack a massive trillion-dollar puzzle. It's the hidden engine that powers pretty much everything you do online, and it's all about making the internet smarter, faster, and way more efficient, one tiny, critical decision at a time.
You know, we all talk about the cloud, but it's not some fluffy thing floating up in the sky. Nope, it's very, very real. It's housed in these enormous data centers, basically warehouses packed to the gills with millions of powerful computers. Every app you use, every website you visit, it all lives right here. And each one of these computers is called a host. These hosts are workhorses, constantly running countless different jobs, which we call virtual machines, or VMs. Think of it like a city's power grid, right? The challenge isn't just about having enough power, it's about getting that power exactly where it needs to go, efficiently, without wasting a single drop. And for the cloud, that distribution problem is just a monumental challenge.
Which brings us to what is essentially the world's most high-stakes, high-speed game of Tetris. How do you fit all these different-sized jobs onto these physical computers in the most efficient way you possibly can?
Now, this game has a technical name, of course. It's called virtual machine scheduling. It's the whole process of deciding which host gets which task. And if you get it right, the entire system just hums along beautifully. But if you get it wrong, well, you end up with massive amounts of waste and inefficiency.
And that waste has a name too: stranded resources. Just imagine you've got a host with a little bit of memory left over but no computing power, or maybe the other way around. That leftover bit is stranded. It's completely wasted because it's too small or too lopsided to be used for the next job that comes along. And this waste, it adds up, costing an absolute fortune in energy and unused computer capacity.
So, to solve this, researchers at Google took a really deep look at the tasks themselves, and they found something pretty surprising. Get this, a whopping 88% of all virtual machines are short-lived. They run for less than an hour. So your first thought might be, okay, let's focus on managing all these little guys.
But here's the brilliant twist. If you look at the total work being done, the actual computing hours, the picture just flips completely on its head. It turns out that 98% of the resources are being used up by that tiny fraction of VMs that run for an hour or more. So think about that. While most tasks are just quick sprints, it's the marathon runners that are using almost all the energy. Misplacing even one of them is a total disaster for efficiency.
Now, this insight led to a really smart idea for scheduling. But, as it turned out, it was an idea with a big, fatal flaw.
The old solution was based on something called one-shot prediction. Basically, when a new task showed up, a model would take a guess at how long it would run. Then the scheduler would try to group tasks with similar predicted lifetimes together. You know, kind of like putting all the one-hour jobs on one computer and all the 24-hour jobs on another. It's a logical approach called lifetime alignment. Makes sense, right?
Well, here's the fatal flaw. Even with a tiny 1% chance of being wrong, just 1%, if you pack a host with 70 tasks that you think are short-lived, there's actually a greater than 50% chance that one of them is really a marathon runner in disguise, and that single mistake ties up the entire host, creating waste and preventing that computer from ever becoming completely free for new work.
And this is where the real breakthrough comes in. The new thinking wasn't about trying to make a better single guess. It was about stopping the guessing game entirely, and instead starting to adapt. The key question they asked was this: what if predictions weren't just a one-and-done deal? What if they could actually learn and update themselves based on what's really happening right now?
And this right here illustrates the core concept perfectly. Just look at this graph. When a task first starts, its average expected lifetime might be really short. But if that same task is still running a day later, what we believe about its future completely changes. Its expected remaining lifetime is now way longer. And after 7 days, well, now it's predicted to run for another 10. The system learns. The longer something survives, the more likely it is to keep on surviving.
This whole idea of adaptive thinking is the foundation for a brand new system, a really clever solution called LAVA.
So LAVA stands for Lifetime Aware VM Allocation. And unlike the old way of doing things, it doesn't just predict once and hope for the best. No, it constantly reevaluates and repredicts how long tasks are going to run. This lets it correct for those inevitable early mistakes that used to cause so much chaos.
And this leads to a fascinating and honestly pretty counterintuitive strategy. Remember, the old way was all about putting similar lifetimes together. LAVA does the exact opposite. It'll often take a really short-lived task and deliberately place it on a host that's already running a very, very long-lived one. So why on earth would it do that?
It's actually brilliant. The host's fate is already sealed by that marathon runner task, right? We know it's not going to be free for a long time anyway. So by filling in the empty gaps with short tasks that'll finish way before the main one does, Lava can use that space efficiently without pushing back the date when the host will finally become empty. It's just a super clever way to max out usage without making the fragmentation problem worse. So that's the theory. Does this adaptive, kind of backwards-sounding approach actually work in the real world? Well, the results are in, and yeah, they are seriously impressive.
In production tests, this new system increased the number of completely empty hosts by up to 9.2 percentage points. Now, that might not sound like a huge number, but in a data center with 1 million computers, we're talking about tens of thousands of machines completely freed up. That's a huge deal.
And the results were incredibly consistent. You can see here, across 24 different real-world environments, Lava, that's the green bar, consistently outperformed the old state-of-the-art method, which is in blue. It just worked better everywhere they tried it.
And the benefits go way beyond just getting more empty hosts. It led to a 3% drop in wasted CPU, a 2% drop in wasted memory, and even a 4.5% drop in these disruptive VM migrations that are needed to clean up messes. It's just a win-win-win across the board. Okay, so let's zoom out for a second, because this isn't just some technical victory for engineers. This is really about building a smarter and, frankly, a greener cloud for every single one of us.
So why does this actually matter to you? Well, first, less energy waste means a greener, more sustainable internet. Plain and simple. More efficiency helps lower the cost of cloud services, which is great for businesses big and small. Having more empty computers ready to go means critical security patches can be rolled out way faster. And finally, fewer disruptions mean the apps and services you count on every single day become more stable and more reliable.
In the end, this whole story is really about the power of learning from your mistakes. Lava created a system that doesn't need to be perfect from the get-go. Instead, it's designed to adapt and get better over time. And that leaves us with one final thought. What other really complex systems in our world, things like traffic grids or global supply chains, could be completely transformed if we just stopped trying to guess the future and instead built them to learn from the present?